Assalamualaikum warahmatullahi wabarakatuh. Today our group will present about the linear motion of the experimental physics.
My name is Muhammad Fazarin bin Talha and my metric number is 2023 454 236.
My name is Muhammad Hakim Riza Ul Haq bin Muhammad Faizan. My ID student is 2023-809-248 and I'm from class 1M.
Hi, my name is Muhammad Iznurizal bin Mokhtar. My ID number is 2023-838106.
Okay, first, we go to our objective of the experiments. That is to use linear air track to investigate Newton's second law of the motions. Then we go to our setup apparatus of this experiment. Our apparatus consists of the air track rail, blower, pressure tube, gliders, flag, photo gates, meshes, mesh hanger, string, and pulley. As you can see, there is the schematic diagram of accelerating system that we have used. Then we go to our procedure experiment. First, you have to assemble the linear air track set as shown in figure 4.1. Procedure 2 is switch on the pump and let the air blow through the track for several minutes. Balance the track by adjusting the screws on the legs of the track so that the glider stays stationary and does not glide to either end when let go. Procedure 3 is insert one hook at the end and a flag on top of glider. Number 4 is measure and record the mass of the hanger and length of the flag. Procedure 5 is attach one end of the string to the hanger and the other end to the glider. And number 6 is place meshes with a mass of 20 grams on the hanger and put the string over the pulley. The procedure of number 7 is position of the glider exactly before the photo gate. Release the glider and record the time shown on the photo gate. And the addition note is, in order to avoid meshes from crashing to the floor and scattering, you have to catch the glider with your hand before the hanger reaches the floor. Procedure 8 is repeat 2 more times to obtain the time average values. And our lastly of the procedure is number 9, that is repeat the procedure 4 more times with 20 grams each added to the hanger.
This is the result we got from the experiment. We got length of flag or S is equal to 0.1 plus minus 0.05 meter. And we got mass of hanger or M1 equal to 0.02 plus minus 0.01 kilogram. And that is the experimental data we got from the experiment. Move to the next slide, which is analysis. The first analysis is plot a graph of weight force versus acceleration A. And you can see the graph right there. We got the gradient is 4.271. The second analysis is, what does the graph tell us? The weight of the hanger and slotted mass plotted against acceleration in reverse, the force acceleration linked visually. Specifically, a graph showing a straight line through the origin signifies a direct relationship between weight force and acceleration. The line steepness indicates the system mass supporting Newton's second law, that is F equal to ma. A consistent slope throughout the graph denotes a steady system mass under applied force. Consequently, this graph confirms theoretical prediction and offers a numerical grasp of experimental result, enabling assessment of the system's behavior across barriers. The third analysis is, do these results support Newton's second law? The absence of a line passing through the origin indicates that the graph doesn't fulfill the criteria. When a graph forms a straight line that passes through the origin and maintains a constant slope, it corroborates Newton's second law, F equal to ma.
4. Discuss any sources of error. Numerous potential error sources could influence the experiment's precision. Unaccounted for friction within the system might impact acceleration measurements, while air resistance, particularly in high acceleration scenarios, could introduce errors necessitating meticulous control of experimental parameters. Inaccuracies arising from time, mass, or force measurements might contribute to discrepancies in calculated acceleration values, guaranteeing stability in the experimental setup, particularly with the hanger and slotted masses, is crucial to prevent deformation during testing. Moreover, minimizing parallel errors, like misreading instrument values, is vital to elevate the overall data precision. For discussion, the graph illustrating the relationship between the weight of the hanger and slotted masses and their corresponding acceleration doesn't intersect the origin as anticipated, suggesting a systematic offset of constant force acting on the system regardless of mass present. This offset hints at potential systematic errors affecting the baseline force measurement. Friction likely plays a significant role in introducing consistent resistance to motion and potentially impacting acceleration precision, leading to a non-zero y-intercept and influencing data interpretation. To address this discrepancy and improve the experimental setup, a thorough exploration and mitigation of potential systematic error sources are vital. Examining the system for initial tension or constraint contributing to the observed offset is crucial. Implementing measures to minimize friction, like appropriate lubrication or adjusting the experimental setup, becomes crucial to align the graph with Newton's second law expectation. Identifying and rectifying these errors are crucial not only for this experiment's accuracy but also for ensuring broader data validity. Furthermore, careful attention should be paid to other experimental variables, such as instrument calibration, which can also lead to deviation from the expected linear relationship. Throughout, calibration and instrument checks are essential to minimize potential measurement errors and enhance overall data precision. Continuously refining experimental procedures, systematically addressing errors, and validating measurement instruments are indispensable for upholding the reliability and integrity of the study's findings. For conclusion, in summary, this experiment utilized a linear air track to investigate Newton's second law of motion, aiming to establish a direct connection between the weight of the hanger and slotted masses and their respective accelerations. The resulting graph exhibited a consistent linear trend. However, its deviation from the origin indicated a likely systematic offset or constant force within the system. This discrepancy, primarily due to factors like friction, introduced a potential systematic error affecting the baseline force measurements. To align the experimental outcomes more closely with theoretical expectation, essential measures involve reducing friction and finally turning the experimental setup. This observation emphasizes the necessity of comprehensive error analysis and systematic refinement of experimental protocols when studying Newton's second law. Key aspects include identifying and mitigating systematic errors, such as minimizing friction and accounting for potential inertial tensions, which significantly contribute to enhancing the accuracy and reliability of experimental results. Additionally, meticulous attention to instrument calibration and rigorous checks is crucial in minimizing measurement errors, thereby improving overall data precision and upholding the study's integrity. This comprehensive approach underscores the iterative process of experimental science, continuously striving to refine the experimental setup and address potential error sources, ultimately strengthening the robustness and validity of conclusions drawn from the data. Future research should focus on further enhancing the experimental design to minimize systematic errors and enhance measurement accuracy, particularly within the framework of a linear air track setup. That's all from us. Thank you for your time.